term here. There we go. That looks good. Yes. Cool. We're live. Well, we were live 10 seconds. We were live like 30 seconds ago.
Okay.
Should we do the intro again?
Sure. Right, so welcome to the School of Maths, UNSW, test preparation for Calculus Test 2.
Calculus test number 2.
Yes.
This is combined 1131 and 1141. So we'll go through these questions. We've selected a few from the purple book. We'll go through them as if we were doing the tests for real. So this will be quite different to what you would see in a lecture or a tutorial. We're just going to do these questions as if we were doing them in a test. So you'll see some examples of the math you understand already, but also some exam style. Cool.
Okay. For the record, I'm Joshua, and this
Hello.
is Daniel.
Cool. First question. Find the equation of the tangent line to this curve at this point. Now, the last thing you want to do with a question like this is to actually draw this curve. Do not attempt to draw the curve, just apply the formula for the tangent line to a curve at a point, which is this. Not that, f of x at the point, say, x0, y0 is y minus y0 is d. So this is the familiar equation of a line. It goes through the point y0, x0, or x0, y0, and this here is the gradient which we need to extract from the curve. So most of this stuff is already given to you in the question. You know what the point is. So x0 and y0 are 1 and 1. We just need to find the derivative of this curve. But it's somewhat strange because this is actually a strange looking curve. It's not in the form y equals some function of x. It's some other beast. So really this should be a function of x and y. And to find the derivative of this curve, we will use implicit differentiation. So I'll just take the derivative of this. So the derivative of this whole curve with respect to x that. Take the derivative of the left-hand side and the derivative of the right-hand side. Good. So the derivative of x squared is 2x. The derivative of y cubed with respect to x. I can't do the derivative of y cubed with respect to x. I can only do it with respect to y. So I will. And I will adjust like so. So this becomes d dy, and the derivative of y cubed with respect to y is 3y squared. This one, I need to use the I need to use the product rule here. So I can do d dx of x squared, so that's 2xy, and the derivative of this is x squared times dy dx equals the derivative of 1 with respect to x, which is just 0. Now I collect my dy dx terms, so this is dy dx times 3y squared minus x squared, and my other terms, which I might collect over the other side here, is equal to 2xy minus 2x, and so dy dx of x, which is a function of x and y, is equal to 2xy minus 2x all over 3y squared minus x squared. What an odd derivative. But this is all I This is all I need. I plug all this stuff into my original equation. So I'll just keep that derivative down there. Hence the equation of the tangent line is y minus y0 is 1, which is equal to this derivative evaluated at the point 1, 1. So I plug 1, 1 in here, so that's 2 minus 2, which is 0, and the denominator is 3 minus 1, which is 2, so 0 over 2 times x minus x 0. That's nice. That whole thing goes away. Well, that's a 1. And it all goes away, and the derivative, or the equation of the tangent, is just y is equal to 1. What a nice tangent. So the question got a bit strange as we were computing this derivative, but it was just an implicit differentiation. The formula you know for the equation of a tangent line to a curve still holds, just the gradient was a bit difficult to calculate. It required some first year mathematics.
Yeah, so cool. Nothing to discuss with this one. All looks good to me.
Yeah, we could try and draw this curve later on if the stream demands it, but you don't need to do that for the question.
Alright, so now I'm going to answer this question. So the question has two parts to it. First part is just to state the mean value theorem. So tell me what the mean value theorem means. And then find a point which satisfies the conclusion of the mean value theorem for this function and this interval. So let's just start by stating the mean value theorem. Right. So the mean value theorem states that if we have a function f, I'll say f of x is, oops, don't watch my handwriting. So if this is continuous, on the interval, so let's say that explicitly, so on the interval A, B, and because I'm getting close to the bottom, I'm going to continue up here. So it's continuous on the interval A, B, including the endpoints, and differentiable on the interval A, B, not including the endpoints, then the theorem promises me one thing. It promises me that there is a C, some value C, in the interval A, B, not including A and B, such that f of B minus f of A of B minus A is equal to, well, it's equal to the derivative of f. It's equal to the derivative of f at some point in the interior. So that's what the mean value theorem says. It says, I promise you can find a point like this. So what we want to do is we want to, for the function x cubed minus 2x squared plus 5 over the interval 0, 2, just find a point one of the points which is guaranteed by this theorem. Alright, so let's firstly calculate what f of b minus f of a on b minus a is. So, for the given function f of 2 minus f of 0 and 2 minus 0. Well, just plug it in. We get 2 cubed is 8, minus 2 times 4, that's also 8, so 8 minus 8 is 0. So f of 2 is 5. Plug in x equals 0, well this is 0, this is 0, this is 5. So I get 5 minus 5 over 2 minus 0, that's 0. So we're looking for a point in the interval 0, 1, which has derivative 0. Right. So let's just note that the derivative of this function is just going to be 3x squared minus 4x.
Problem solved. We just had it over twice.
Okay. Now should I leave the question or write it out? Okay. Well, let's write it out.
Let's wrap it out.
Yeah. Right, so what we need to do is we need to find a c in 0, 1 such that this quantity, sorry, c in 0, 2 such that this quantity is 0. So we're looking for f prime of c, which is 3c squared minus 4c equal to 0. So that's equivalent to looking for c times 3 minus 4c equal to 0. So say it that way, i.e. looking for that. Now, if we're looking at this, I can actually see two solutions to this. So, well, if I'm just looking for this equal to 0, forgetting why I was looking for c, this equal to 0, I would come to the conclusion that c was equal to 0 or c was equal to 3/4. So these both give me derivative of f equal to 0. But, well, this wasn't the one that was promised to me. I was promised one strictly inside the interval 0, 2. So this thing is not in 0, 2, it's just in the boundary, and this thing here, well, this, so since 3 over 4 is actually inside the interval 0, 2, it is the, so it is the value that we were promised.
You've just this bit is
thanks.
swapped around.
So I have. Thanks. Right. So
Doesn't change it too much.
Yes. Luckily, this point still is inside, but wrong point. All right. So yes, since 4/3 is in the range 0 to 2, this is the value. Well, it's the value guaranteed by the theorem.
MBT.
Yeah.
Cool.
So that guaranteed by the mean value theorem. So yeah, do watch your algebra. It's very easy to lose your way.
No, it's a nice question and really kind of highlights the fact that the MBT only guarantees that some C exists. It doesn't actually tell you what it is. You have to work a bit harder for that. Sometimes it's actually very difficult to find the C, but in this case, finding C was possible. Cool. Here it is. All right. Next question. Okay, so here we have a 2-mark question. So far the questions have all been 2 marks. And the purpose is just to apply the definition. So we will straight up apply the definition of the derivative to this function and confirm that it is indeed what we want it to be. So this requires you to know what the formal definition of the derivative is, which is the following. It's actually a limit as h goes to 0 of f of x plus h minus f of x all divided by h. It's a good idea to start with the actual formal definition, and now we'll just plug in what we know f of x is. So of f of x plus h, that's negative x plus h all cubed. So just applying the definition of f to this thing called x plus h minus negative x cubed all over h. Alright, so I can expand this, and if you don't remember how to expand this, it looks something, well, the Pascal's triangle can help you. So remember that the coefficients can be determined like this. You start with 1, then you just kind of expand this triangle with 1s down the diagonal, and this bit here is the sum of the 2 directly above it. So I want the next one down, so I start with a 1, 2 plus 1 is 3, 2 plus 1 is 3, and I have a 1 on the edge there. And this gives me the coefficients I require to expand x cubed. So this is negative. This thing is, the first coefficient is 1, so that goes out the front of x cubed. The next one is 3, so that's x squared, the coefficient of x squared h. The next one is a 3 again, so x h squared this time, and 1, so that's just h cubed. Minus x3, so that's plus x cubed. Plus x cubed. All divided by h. And the nice thing that happens, and this will happen every time you have one of these formal definition questions, is the terms without any h in them whatsoever will cancel. So I can write this whole thing as the limit as h approaches 0 of the remaining terms, which is negative 3x squared. Maybe I'll take a common factor of h out of this. Plus 3xh plus h squared times by h all over h. And again, that will now cancel with that. And again, this is what's going to happen every time you have one of these questions. You can expect those terms to disappear, you can expect the h to cancel with one of the h's up there. And now I can just substitute in h equals 0. And I get left, well that goes away, I just get left with that term. So this is negative 3x squared, which is exactly what I was expecting it to be all along. But we've confirmed that with the formal definition of derivative. Cool.
Let's see.
Anything you'd like to add?
I think we've lost a few minus signs along the way.
Oh, I have, yes, absolutely. Thank you. Minus.
So we got a minus 0, so plus 0. Okay, cool. That's a nice application of just directly finding a limit to get a derivative. So So, actually my next question. So for my next question, I want to find the limit as x approaches 0 of 1 minus the cosine of 3x over x squared. So you can probably guess by looking at this. You can guess by looking at this. This top term is going to tend to 1 minus the cos of 0, or 1 minus 1, which is 0. Bottom term obviously also goes to 0, so it looks like a prime candidate for using the Hospital's rule. So I'm going to make the assumption that the Hospital's rule is going to work for me and just push through this. Right. So, limit, as x approaches 0 of 1 minus cos of 3x over x squared. Well, if the Hospital's rule is valid, this will be the limit as x approaches 0 of the derivative and the top and the bottom. So if I take the derivative of the top, I get 3 times the sine of 3x. Just remembering that the derivative of cosine is minus sine, so the sign has changed. And the derivative of the bottom is 2 times x. And since I was using Hospital's rule, I'm just going to put the reason by Hospital's rule. Now, actually, just looking at this, I still can't just work out the limit because sine of 3x as x goes to 0 is also 0. 2x, well, that also tends to 0. So this is another prime candidate using Hospital's rule. So if it finally works, the Hospital's rule is always dependent on whether or not the final limit does exist. But if it works, it'll be a derivative of this, which is 9 cos 3x, so 3 times 3, over 2. Right. And this one, actually, this limit I can evaluate, because this is a constant 2, and the top tends to 9 cos 0. 9 cos 0 is being 9 times 1, or 9. So this is just going to be 9 over 2. So yes. So since this final limit did exist, it means my previous applications of the Hospital's rule were all valid. So by Hospital's rule, this limit is equal to this limit is equal to this, and therefore this limit is equal to this. So potentially I might want to just explain that again. From this step to this step, I was trying to apply the Hospital's. Right. So if I had failed, if this didn't actually exist in the end, then that means everything I was doing up to this point was never actually working. But since it did exist, this is actually a valid argument, proving that the limit is 9 over 2. And again, this is a 2-mark question.
Yeah, so we never really knew if we were on solid ground here. This was kind of a leap of faith. We didn't know if this limit or this limit existed until we found, well, we didn't know if this one or even this one existed until we found that this one existed, and then just the Hospital's rule guarantees that all limits above it exist. I would have added something about being 0 over 0 or infinity over infinity, because you can only apply the Hospital's rule in those cases. So something simple like a 0 over 0. So since is of form 0 over 0. Not actually 0 over 0, but this is a kind of compact way of stating that the top and the bottom are both going to 0, and hence we're in the ballpark for using L'Hopital's rule. And Josh mentioned that, but I'd make sure to write it down, something along these lines. Infinity over infinity also works.
Yeah, there's no talking in the test, so you have to write it.
Cool. Excellent. Here we have a very verbose 2-mark question. If you're wondering what's the deal with mathematicians and writing questions like this, well, mathematicians have been writing questions like this for thousands of years. They're all clay Babylonian tablets with questions about ladders leaning against walls in them. And hence we continue that tradition for many thousands of years by asking you questions about ladders leaning on walls. Here is your question. A ladder of length 3 meters leans against the wall, and the foot of the ladder is being pulled away. So let's draw a diagram of what's going on here. Here's our wall, it's vertical, our floor is flat. Let's call this, let's just leave it like that, shall we? The ladder is 3 meters long. So here's my ladder, like this. And that length there is 3. Let's call this, well, let's just keep reading first. The foot of the ladder is being pulled away at a rate of 1/2 meters per second. So if this point here is x, then dx dt is equal to 1/2. It's going this way at 1/2 meter per second. So implicitly there's a time here. So this position x here is really a function of t. How fast is the top of the ladder moving? Well, let's call this thing here y. When the ladder is 1 meter away from the wall. Okay? So the first thing we need to do is somehow relate x to y, and of course we use Pythagoras' theorem to do that. Since x squared plus y squared is equal to 9. Alright? We're asked to find dy dt. Now the last thing you want to do is express this as a y as a function of x. It's much simpler just to take the derivative with respect to t. So I'm going to use my implicit differentiation and take the derivative of the whole thing with respect to t. dt of x squared plus y squared is equal to d dt of 9. Now remember, x and y are both functions of t, so they have some kind of meaningful derivative, but 9 is not a function of t, so its derivative is 0. This thing here is d dt. I want to take the derivative of x squared with respect to t, but I don't know how to do that with respect to t. I only know how to do that with respect to x. So I adjust like so, and similarly over here, dy dt times 2y is equal to 0. So I want to know what the value of this is when x is equal to 1. This is always a half. I need to know what y is. When x is equal to 1, dx dt, well that's always equal to a half, and y, when x is equal to 1, well y squared is 9 minus 1, which is, so y is equal to the square root of 8. And I'll demand it's equal to the positive square root of 8, not the negative square root. Hence, I'll just substitute all these things except dy dt, but I'll find out what that is in a minute. This is 1/2 times 2 times x is 1 plus dy dt times twice y, which is 2 root 8, is equal to 0. And so I'll bring all this stuff over to the other side, and dy dt is equal to, that's just negative 1 on 2 root 8, which I might simplify a little bit to be equal to, what is that equal to? Root 2 on 8. Cool. Okay. So maybe I'll just say a few words about this while you're writing up your question. This question was made significantly easier by not taking the square root and isolating y as a function of x. You could use your implicit differentiation to do this question without much easier in this way. second of all, diagram really helps with a verbose question like this. Part of the question is actually extracting the math out of this paragraph into a diagram and therefore into symbols that you understand. So there's some real work to be done here in correctly translating and interpreting the question.
So one more part of the sentence. Right, so this is the question I'll be answering. This is actually a 3-mark question. So you can tell it's probably going to be a little bit longer than maybe the latter question. So we want to, well, we're given this piecewise defined function. So when x is less than or equal to 1, it's just a linear function, but we have some free coefficients which we can play around with. And when x is between 1 and 2, it looks like the tan of x times pi over 4. So tan acting on x pi over 4. And we have to find all values of a and b such that this function will be differentiable at x equals 1. So again, for this sort of thing, you don't need to plot this thing. You need to understand what the requirements are for this function to be differentiable. So step 1, I need to make sure that this function is actually continuous at x equals 1. If it's not continuous at x equals 1, it has no chance of being differentiable at x equals 1. So let's ensure continuity first. Right. So to ensure that f is continuous, I should write continuous fully. So let's ensure that f is continuous at x equals 1. We'll examine this. So the limit, the limit as x approaches 1 from the left of this function f of x. Well, if we're solely approaching, that's more greater than. Wait, this is incorrect. The question actually says that it looks like this x less than or equal to 1. So if we look at the limit as x is approaching from the left, well, to the left of 1 it looks like ax plus b, so this is the limit as x approaches 1 from the left, ax plus b. And well, that's an easy limit to compute, it's a plus b. And we'll also look at the limit as x approaches 1 from the right, f of x. Well, if it's approaching from the right, so it will look like this function, the tan of x pi over 4. So limit as x approaches 1 from the right. It's the tan of x pi over 4. So that will be just the tan of pi over 4. And hopefully we can remember that tan of 45 degrees is actually 1. Yes, you want to remember the basic triangle, it's a 1, 1, root 2 triangle. Right. So to ensure that this limit exists, we must ensure that a plus b is equal to 1. Meaning we require a plus b equals to 1. Alright, so that gives us a condition, but it's not enough to pin down a and b entirely. This is only ensuring continuity. Now I need to make sure that the derivatives match. So there's a nice theorem that says, because these functions are continuous around 1, I can just, so these functions are differentiable around 1, I can just look at their derivatives and match those up. Right, so for differentiability, Well, I'm going to require that the derivative of ax plus b, that will have to equal to the derivative of the tan of x pi over 4 at x equals 1. So derivative of the left-hand side, I'm requiring that a will be equal to derivative of tan. Well, I hope you remember that derivative of tan is sec squared. At least you can try and rewrite things in terms of causes and sines, that's more helpful. But if you do remember the derivative of tan is sec squared, you can save yourself a bit of time here. And then also times the derivative of the argument, that is pi over 4. So at x equals 1, that means a will have to be equal to pi over 4 sec squared pi over 4. Sec squared is 1 on cos. The cos of pi over 4 is 1 on root 2, so this is going to be 1 over 1 on root 2 squared. But the upshot is, if you work it out, you'll find it's just 2. So it's 1 over a half. So that means I need a to be equal to pi over 2. And I'll feed that information back in to get b. So I already had that a plus b was 1. So hence b will have to be 1 minus pi over 2, just to satisfy this equation. So this ensures continuity, and this will ensure, well, these two ensure differentiability. So it's actually unique. There's only one line you can take, match up with the tan function and make it differentiable.
Cool. I might mention that there's a theorem that tells you can do this in order to make sure a piecewise differentiable curve, a piecewise defined curve is differentiable at the point at which they join. You just need to make sure that they match up at the point, so they're continuous and their derivatives match up at the point. So they join and they join smoothly, and that's all you need to do. You can also, I don't recommend doing this, but you can also use the formal definition of the derivative at the point where they join, and that will tell you how to find a and b, but it's much simpler just to go through and check that they're continuous and check that the derivatives match. So that's the nice thing about doing this for piecewise defined curves. So this is the final question in the stream. It's worth 3 marks. Part 1. So I'm defining this function on the closed interval 0 to 5. And part 2. Good. So I might start off this question, part I, by reminding you the definition of a critical point. So, So a critical point C is something in the closed interval AB, and critical points occur in three possible flavors, either C equals A or C equals B. The endpoints of your interval are all critical points. So there's two critical points straight up. C. The next one is either F is not if the function is not actually differentiable at the point where x equals c, then that's a critical point too. So this also encapsulates points where the function is not continuous. And thirdly, this is probably the one you're most familiar with. The stationary points. They're critical points too. So there's three flavors of critical points. We're just asked to enumerate them. The fastest and therefore best way to do that is just to draw the graph. That's x, y. So my function is the absolute value x squared minus 2. So I'll remind you that x squared minus 2 goes through the points. There's could be 1, 2, 3, 4, and 5, like this. X squared minus 2 is a parabola going through here, going through 0 and going through 2. And the absolute value of that is I just make the whole thing positive. So it goes something like this. Like that. So the parabola. So anything that was negative I just reflected. And this is the graph of y equals absolute value of x squared minus 2. I'm not sure about that. Oh, sorry, have I written down the question correctly? That's x squared minus 2x. I have to go through root 2. So I have to go through root 2 over here and negative root 2 over there. So it ends up looking something like, when x is 0, this is 2. So I go like that. Have I written down the question correctly? I thought this was x squared minus 2x. In fact, I think I prefer the question as x squared minus 2x.
Just put it all out. Yeah, x squared minus 2x is the question.
I do want x, sorry, that's x squared minus 2x. Like that. Good. So, there we are. There we are. Good. This is a more interesting question. You get the full complement of critical points this way. Good. So let's just enumerate what the critical points are. Endpoints. X is equal to 0 and x equals 5. I like to just say what flavor of critical points I've got, just to make sure I get all three categories covered. The next one is the points where f is not differentiable, and I can see, just based on my graph, that the function is not differentiable here. It's continuous, but the slopes certainly don't match. So, at x is equal to 2, and there's a stationary point here when x is equal to 1. So I'm just going to list off my critical points. The second part of the question asks you to find the absolute maximum and absolute minimum values of f on this interval. Now, I'll remind you the absolute maximum and absolute minimum values are the upper and lower bounds of the function, which are actually achieved in this interval. And the max-min theorem tells you that the function will actually achieve its maximum and it will achieve its minimum on this closed interval, but it doesn't tell you where to find them. It doesn't tell you what they are. The good news is for a continuous function, they always occur at the critical points. So for part B, since f is continuous, on 0 to 5, the absolute minimum, so all I need to do is check what f does at the critical points. Since f of 0 is equal to 0, f of 1, well I better check f of 1, that's 1 minus 2 absolute valued, which is 1. F of 2 is 0 and f of 5 is equal to, well, 25 minus 10 is 15. Then I know what the absolute maximum and absolute minimum values are. It's 0 and is 15. And so I can annotate my graph a little bit more. That's the point 5, 15. There's the point 0, 2. Well, it's obviously 0, 2. Here's the point 1, 1. 0, 0. Cool. And just based on my graph, I see the function does actually achieve its maximum value here of 15 at x equals 5, and its minimum value here at 2, and again at 0. So my what I was promised by what I know about continuous functions and critical points is actually also true just by looking at the diagram. Cool.
So one thing I might just draw people's attention to again. So actually, these square brackets are very important. It was very important that it's continuous on the closed interval. You have to. If you don't have the endpoints, there's no guarantee. So the endpoints are very important.
Absolutely. If I change this to an open bracket, then the function does not actually achieve its lower bound, its upper bound of 15 here. So I can't say that 15 is a absolute maximum because the function doesn't get to 15 because the function is not permitted to, or it's not defined at x equals 5. So yeah, absolutely, the closed interval is critical of this, and critical points are all defined in this way as well. Cool.
Right. Well, hope you enjoyed that. Unfortunately, it looks like there's only 10 people watching, so thank you for watching in the future as well.
Cool, and we'll see you all next time. There'll be another live stream for the algebra class test later on in the semester, and one more for the final exam. So, thanks for watching. We'll see you next time.